Okay, so now we can pick up where we left off last time with our introduction to derivatives. And what I'd like to do is go back to the beginning of 2.2. We just barely started this. I want to start at the beginning so we can look at all these different rules that we need to know and get some practice with them. So we'll start out with the constant rule, which is the easiest one of them all, of course, because the derivative of a constant is just zero. Why is that? Because the derivative is a rate of change. And therefore, because this is a constant that doesn't change, it must have a value of zero. So now keep in mind with the notation, there are many different ways of expressing a derivative. The ones we're going to see most often are f prime of x and dy dx. There are others, but these are the ones we'll see most of the time. Now, sometimes it's more convenient to use f prime of x. Sometimes it's easier to simply use dy dx. It depends on what the application is. So here they're going to use the dy dx notation. So the way they do it is this. So if this is the derivative, what they'll do is replace this with d, and then in parentheses, whatever it is we're differentiating. In this case, it's a C, and that's equal to zero. So this is referred to as the constant rule. All right. So what comes after the constant rule? And then they have several examples here, of course, which we've already seen. This is really maybe one of the more important ones. It might be the most important one, but certainly it's way at the top of the list. The power rule. So this is what we're going to use when we run into a polynomial. Um, Here, for example, we have very simply x to the n. And how do we take its derivative? So x is raised to the n power. The derivative is n times x to the n minus 1 power. Okay. So if, for example, you had something like this, in this case, n is 4. So you'll end up with 4x to the 4 minus 1, which is 4x cubed. And it's that simple. Okay. All right. So far, so good. Now, here's some other examples. For example, what if we have f of x is x cubed? So we can write, now here they're using the prime notation. So it's just, since this is n, we start with the n, then we have x, and then the exponent becomes n minus 1. Then they have g of x is the cube root of x. For something like this, you probably should rewrite it as x to the 1/3 power to make it more obvious what you're supposed to do with it. And when you subtract 1 from 1 minus, sorry, 1/3 minus 1, you'll end up with negative 2/3. Okay, so you got to be careful with those fractional exponents. Okay. And then they also have y is 1 over x squared. So again, you might want to rewrite this. Oh, sorry. Y is x to the minus 2 power. So now they're going to use the dy dx notation, and we'll end up with minus 2x. Now, when you subtract 1 from minus 2, you end up with minus 3. And that's how they work. And then at the end here, what they've done is they've rewritten it, if you choose to do so, as minus 2 over x cubed. It's not necessary, but that's what they did. All right, now what's next? Constant multiple rule. Now, imagine extending this a little bit to the following. You're basically combining the first two rules. if instead of x to the n we have cx to the n, where c is a constant, n is an integer, most likely. The n doesn't have to be an integer, but it often is. Then the derivative is c times um, n x to the n minus 1 power. Now they wrote it as c times f prime of x. I think they wanted to do it in a more general way. Um, let's just rewrite it like this. When you're dealing with the power rule, this is what you're going to wind up with, but they want you to see that this could be applied to any uh, rule. The idea here is that all you're really doing is factoring out the c, and then you apply whatever rule you need to solve for f prime of x. Okay. So let's try this one. Y equals 5x cubed. So now here's our constant, here's our n. So according to this rule, we're going to have c n x to the n minus 1. Okay, or 15 x squared. Okay, so that's what this is telling us. They also have 2 over x, 2x to the minus 1. And so we do the same thing. The constant stays on the outside. Then this piece, for this, we have a derivative of negative x to the minus 2 power. And they are rewriting it like this. Okay. And then they love to change the letters sometimes. F of t is 4t squared over 5. And the 4/5 is the constant. You might want to rewrite it like this. So when you differentiate it, you'll have 4/5, 2t to the 2 minus 1 power, which is 8/5 times t to the first power, which is just t. Okay, now you'll get plenty of practice with this with the WebAssign problems, but this is the kind of thing you can learn it with just, more practice. Oh, they've got plenty more here. 2 radical x. So again, you should probably rewrite it like this so you can see that it is in fact the same rule. So 1/2 minus 1, of course, is negative 1/2. The 2 and the 1/2 cancel each other out, and we end up here, which is the same thing as this. Although you certainly don't have to write it like that. You can leave it as x to the minus 1/2 if you want. Um, what else do we have? 1 over 2. Now here's a tricky one. So let's take a closer look at this radical. What are we supposed to do with it? Well, this is the same thing as x to the 2/3 power. So that's really the key to the whole thing. So what I'm going to do is rewrite this as 2 times x. Since it's 1 over that, um, let's do this. Now, if you do that, you notice how you still have this in the denominator. What you might want to do is rewrite it like this. Actually, I'm sorry. This is not right. This down here, this is positive. But since it's in the denominator, what you actually have here is this. Let's write it like this. And the reason why I'm writing it like this is because then you can see that this is the equivalent of x to the minus 2/3. Okay. Uh, so in other words, 1 over x to the n is the same thing as x to the minus n power. And now we can apply the rule. We have a constant. The exponent is minus 2/3. When you subtract 1 from minus 2/3, it becomes minus 5/3. God, what a mess, huh? Um, these two, 1/2 times negative 2/3 becomes negative 1/3. And if you want, you can rewrite that as negative 1 over 3 x to the positive 5/3. Let's see what yeah, that's what they decided to do. All right, perfect. And then here's a relatively simple one, y equals negative 3x over 2. And you can just rewrite this like this. Keep in mind that x has an implicit exponent of 1. So we can apply this rule again. But now the exponent becomes 1 minus 1. And that's just 0, which means that we end up with just negative 3/2. Ah, tricky. Okay. All right, what do we have now? So yeah, this you can think of this as a single rule. It's the power rule with a constant. That's all it is. Now, you sometimes might find yourself needing to add or subtract derivatives. So let's take a look at this. The derivative of a sum of functions is the same thing as the sum of the derivatives. And you can do the same thing with differences. So this is very straightforward. That's nice. Now, the reason why this is so important is because if you're trying to take the derivative of a polynomial, let's say, x cubed minus 4x plus 5, what you're effectively doing is applying the sum and the difference rules, because what you can do here is you're going to take the derivative of this term, subtract the derivative here, and add this one. So here, this one will be 3x squared from the power rule. Now, keep in mind too, from the beginning, the constant rule, the derivative of 5 is 0. It's already here. And so we end up with 3x squared minus 4. So you used a lot of rules here. You use the addition rule, you use the subtraction rule, you use the power rule, and you use the constant rule, all in that one simple example. What about this one? Minus x to the fourth over 2 plus 3x cubed minus 2x. So we'll do the same thing here. First, let me just quickly rewrite this as minus 1/2 to make it easier to see what you're supposed to do. And then we apply the combined constant and power rule. Okay, so you notice in each case, I have the constant state on the outside. Then I apply the power rule, and I end up here with negative 2x cubed plus 9x squared minus 2. Okay. And then, ooh, we got this. Look at this one. Now I see what they did. All right. So you've got y equals 3x squared minus x plus 1. Now, there is a rule for quotients, but we haven't seen it yet. So what they want us to do is instead write it like this. We'll actually divide x into each of these terms. And this in turn can be written as 3x minus 1 plus x to the minus 1, and then apply the rules that we do know. Now, this one is just 0. So ultimately end up with 3x to the 0. And that, of course, is just 1. So the final answer is, or 3 minus 1 over x squared. Okay. All right. I think that might be it for now. They're going to, ooh, okay, no. What they're doing is they're showing us some quick sine derivative, sorry, not trig derivatives. There are quite a few of them, but the two most basic ones, the ones you'll see most often, are right here. The derivative of the sine is the cosine, but you might think the derivative of the cosine is the sine, but it isn't. It's actually the negative sign. Okay. So just keep that in mind when you do these. And we'll see quite a few others as we go along. Ah, as soon as now. Okay. So, 2 sine x. Okay. Well, the 2 is just a constant. So, in other words, you keep the constant on the outside. The derivative, as you know, of the sine of x is cosine x, and we just end up with 2 cosine x. I guess just for the fun of it, this time they called it y prime. Remember, I mentioned there's multiple ways of expressing a derivative. Um, the two that I showed you, but there's also y prime. I guess I just want to make sure you remember that that means the derivative. Actually, I'll tell you what I'm going to do. Let me move this over here. It just looks nicer. All right, that's good. There we go. And then they have 1/2 sine x. Same thing. It's just that 1/2 is just a constant. X plus cosine x. So we're applying two different rules and adding them together. So here we apply the power rule. Here we know this to be the negative sine of x. So we end up with 1 minus sine x. Okay. And then, ooh, now look at this one. Cosine x minus, now pi over 3 is just a constant. Okay. So don't worry about it. Just you apply it the way you normally do. So we're going to have negative sine x minus pi over 3 times the sine of x. Yeah, sorry, the cosine of x. And that's it. We're done. Okay. Well, that was fun. Rates of change. Now, what they're going to try to do here is we go along is try to introduce some applications of derivatives before we see all of the rules. Um, Rates of change represent the change of one variable with respect to another variable. So here, if you remember, they mentioned this earlier in the course, that if you have a function that represents the position of a particle um, as a function of time, where is it going? Okay, it's some particle. Let's say it's an electron. And so what they're telling us is that over some interval, the average velocity is the change in distance over the change in time, or delta S over delta T. Okay. So what they want us to do is, let's say a billiard ball is dropped from a height of 100 feet. The ball's height S at time T is this. Okay. So basically it looks something like this. That's where the ball is going. You throw it out and it goes out in that direction. So what they're after here is the average velocity over each of these intervals. From 1 to 2. So what do they want us to do? Well, we're going to take um, the change in S over the change in T over that interval. Now, S of 2 is, okay, so I just replaced the T with 2. Now the times are just 2 and 1. Okay, we don't really need a separate function for that. Um, but anyway, here's what we're going to wind up with. All right, what do we have here? Minus 64. The hundreds drop out. Now, that would, of course, refer to the fact that it's falling. That's why it's negative. And because this function is measured as feet per second, that means that so is this 48. So in other words, the ball falls at a rate, or an average rate, I should say, of 48 feet per second. Okay. So yeah, we don't need to do all of these. So velocity, then, because of the way it's defined, and they're using the limit definition here, by the way. Um, if the rate of change is delta S over delta T, then As the t's get closer to each other, notice instead of looking at two different seconds, instead of we're looking at like nanoseconds or something like that. Well, it just so happens that this is the derivative of s with respect to t. Okay. You might recognize that formula. That formula is the definition we use to derive the derivative from a limit. Okay. Now, this could also be written as ds dt. As we've seen, they both mean the same thing. These are both the first derivative of s with respect to t. So yeah, I think we can skip over some of this. Unless you're in love with physics applications, let's go on to 2.3 and learn some new rules. Okay. Now these where they're starting to get a little bit messier, as you can imagine. Okay, we start with the product rule. Now, you would like to think that all you'd have to do is multiply the two derivatives, but sadly, it doesn't work out that way. It's a little bit messier than that. So let's take a look at this. So we're taking the derivative of f of x times g of x. Now, this can be written in a few different ways, um, but this is a fairly standard way of doing it. Oh my God. And of course, you see we're using that prime notation. You don't have to, but it's often done with these rules just to keep it simple. And what do we have here? Well, it's the first function times the derivative of the second plus the second derivative times the derivative of the first. So let's see what kind of examples they have for us. Here we go. So h of x is another function. We're assuming that it is the product of f of x and g of x. Now, we want to take the derivative of h of x by using the product rule. So here's what we're going to do. Rather than doing it on the fly, we're going to write down f prime of x. And of course, you can see we're using the rules that we already know. And that equals, now remember, x to the 1 minus 1 is x0, which is just 1. So it's 3 minus 4x. And then g prime of x would be, so this 5 is a constant. So this one is nothing but 4. Now we have everything we need. We have the definition of f of x, g of x, f prime of x, g prime of x. We can just plug them into the definition from the product rule, and then we'll see what happens. All right, so remember, f of x was 3x minus 2x squared. G prime of x is 4. G of x is 5 plus 4x. F prime of x is 3 minus 4x. Okay, now that is actually that is correct, but Depending on the circumstances, we may go ahead and simplify it a little. When you're doing your WebAssign problems, they may ask you to do that too, to reduce this to a single polynomial. So let's see what would happen if we do that. So over here, we have 12x minus 8x squared. But now we have this part here. Let's move this aside and evaluate it with FOIL. All right, so here we go. There's F, O, minus 20x, I, which is 12x, and then last is minus 16x squared. So when we bring these together, we have 15. These two add up to negative 8x minus 16x squared. Okay, great. Let me just double check real fast. Yeah, we got it. So then you can bring that up here. But we're not done because it's just a random string of terms. We ideally would like to um, combine these properly into a polynomial, which means the order is descending of the exponents. Now, it doesn't seem to want to copy, so I'll do it here. All right, so we'll find all the like terms. We have 12x minus 8x, and then we have one constant, which is 15. And so we can combine these now. And there you go. This is our polynomial. And you notice we write them in descending order of the exponents, and we save the constant for last. Okay. Now, if you notice, that took a while, didn't it? Yes, this is a very messy process, but we need to get used to it. All right, what else do they have for us? Oh, okay. Well, this one involves trig, but that's okay. We can do it. What do we have? 3x squared sine x. All right, so now we can think of this. We can rewrite this as h of x equals f of x times g of x. And if f of x is 3x squared, then f prime of x will be 3 times 2 times x to the 2 minus 1, 6x. And g of x is sine x, which means the g prime, as we've already seen, is the cosine of x. So now we can write out the rule. And then substitute. Great. So we have 3x squared, cosine x, sine x, 6x. Well, this one is pretty straightforward. We can write it like this. Um, Usually when you have a mixed term like this, you write the trig function last. Wow, that one wasn't that bad. All right, 3x squared cosine x. Oh, they factored it out. That's okay. Um, yeah, it's the same thing. All right, good. Now, if there's a product rule, it stands to reason that there's a quotient rule. It also stands to reason that it's messier than you might think. Okay, so let's see how this one works. Okay, so now we have, uh, they're using this notation. Now, of course, we have to assume that g of x is not zero. Yeah, it's a bit messier. All right. So, um, and again, it's the kind of thing you just basically have to memorize it. You should know these by heart. Even with an online class, you really need to know these by heart because otherwise you'll waste all your time searching around for rules. And, you'll probably, maybe if you're doing Calc 2 in the classroom, you're not going to be allowed to do this stuff online. All right, so let's look at an example. All right, here we go. So that means f of x is the numerator, 5x minus 2. So the derivative is just 5. G of x squared plus 1, g prime of x, 2x. All right, so now we can substitute this rule. We'll copy it down here, and we'll just copy everything we need in there. Just neatening it up a bit. All right, here we go. X squared plus 1. Actually, I think I may have messed it up a little. There we go. Perfect. Okay, great. G of x is x squared plus 1. F prime of x is 5. F of x is 5x minus 2. And g prime of x is 2x. All right, so we'll probably should probably just simplify the numerator. The denominator can't really be simplified. So we multiply these. Now be careful here. We are subtracting. So it's easy to miss that negative. Here we have 10x squared minus 4x. And then we'll keep the denominator the same. Unless it turns out that we can factor it or something, which is not likely. And then we'll combine the like terms. We have 5x squared minus 10x squared, so we have minus 5x squared. And then we have the 4x, and then we have a constant, and that's all divided by x squared plus 1 squared. All right, then there's really nothing we can do to simplify it any further. If we could, simplify it, we would, but no, it's fine the way it is. All right. Yeah, so that's exactly how they left it. Beautiful. What else do we have? I think what they're doing here is reproving the power rule in terms of the quotient rule. That's fine. We don't need to deal with this. We already know how that works. Now we've got some more trig derivatives. All right, let's take a look. Now, so again, these, you maybe want to write these down or make up a list or memorize them. Um, we're not going to prove them. That'll come maybe later in the course, maybe in Calc 2. But here we're just going to write them down. Although certainly, if you really wanted to, you certainly could prove these if you say to yourself, listen, I don't like to just memorize. I want to prove this. It could be done. Um, Sometimes it gets very messy, but sometimes if you use a clever substitution, like for example here, how would you prove this? Well, what you would have to do is this. Just remember, tangent x is sine x over cosine x. And in turn, the secant of x is 1 over the cosine. All right, so what I'm going to do is just this one. We're not going to do the others. We're going to use the quotient rule to prove this one. So since f of x is sine x, f prime of x is cosine x. G of x is cosine x, which, as you recall, which implies that g prime of x is negative sine of x. So because the rule, the quotient rule that is this. Now we make our substitutions. Cosine x, cosine x, sine x, negative sine x. Okay, now we have to do a little simplification. Now you may remember, we reviewed this very quickly earlier on, that one of the Pythagorean identities is this. So we actually have 1 over cosine squared of x. And because the secant and the cosine are inverses of each other, that implies that this is nothing but secant squared of x. Ah. So you can see with some clever substitutions, we were able to prove that this is, in fact, the correct derivative. And you could do it with all of them if you felt so inclined. But I thought it'd be fun to see one of them. And then, if you really want to see the others, maybe one day we'll do that. But so we have the derivative of the tangent is the secant. What else do we have? Um, the derivative of the, so let's put this here with the others. For the secant, we end up with the secant times the tangent. For the cotangent, that's the negative cosecant. And then finally, the one that's missing is the cosecant. And that gives us negative cosecant x, cotangent x. And that finishes them up. So the six basic trig functions, we now know all their derivatives to go along with our the original ones. In case you forgot, which I'm sure you did not. And that's it. That's all of them. Okay. Now they've got some examples for us, of course. Y equals x minus tangent x. So this is pretty straightforward. The derivative of x, as we've seen, is just 1. And tangent, as we already know, is secant squared x. So that's easy. What about x? Now x secant x is trickier because, of course, we need the product rule. So here we're going to assume we'll call this h of x. So f of x is x, f prime of x is 1, g of x is the secant. And based on the chart that we just developed, the derivative of the secant is secant tangent. So we'll just plug in everything into the rule. All right. And let's see what happens. Now, here we can simplify it a little because every term contains a secant. And I believe that's as far as we can go. Oh, what happened there? I think something just disappeared. Oh, it got erased somehow. Let's see, X. All right, so that should do it. All right. Higher order derivatives. Now, it's possible to take a derivative more than once. And so here's a quick example from physics. S of t is the position of a particle at a given time. The first derivative is the velocity. And then look what they have there. Um, so I just want to mention here that when you take the derivative, this is actually called the first derivative. because there's more. With two primes, you can probably guess it becomes the second derivative. And then if we do it again, it becomes the third derivative. Now, in practice, while you can take as many derivatives as you want, most of the time we do not go past the second one. Okay, it's rarely necessary for uh, actual real world examples, but they do exist. Okay, it's just that normally we only use the first or the second derivative. It's rare that we need the third derivatives. Now, as far as the dy notation, it's a little unusual. Not exactly what you were expecting. You have to be careful with it. And then with the prime notation, it works very simply. We have y prime is the first derivative. Y double prime, of course, is the second derivative. And that means, of course, y triple prime is the third derivative. So, luckily for us, though, the higher order derivatives just mean you're repeating the same rules more than once. There's nothing else to it. It's just do it again. So, if you had, for example, f of x is 2x cubed minus 4x squared plus 4x plus 5, the first derivative would be using the rules that we know, which brings us to 6x squared minus 4x plus 4. And then the second derivative means you're applying the same rules to the first derivative. All right. In the same way, same rules, same everything. Actually, to be consistent, let me write it like this. All right. Now, by the way, I do want to point out that at least for polynomials, eventually, if you keep doing this, you'll end up with zero. You have to reach zero when you're differentiating polynomials. In other words, f prime cubed, this would be 12. And if there's a fourth one, which we sometimes see written with Roman numerals, it would be zero. So, in other words, this process will stop. For other types, for the trig functions, the process will never stop. But for polynomials, eventually you will reach zero. That'll prove to be significant, by the way, down the road, that idea. Yeah, look at all those notations. Oh my God. Yeah, they send it all the way up to n, and they, of course, all mean the same thing. Yeah, so yeah, here's a physics. Oh, let's run with this. This is that position, that function that we saw earlier, the position of a particle or a moving object. S of t is negative 0.81 t squared plus 2. So the velocity, as we saw a little while ago, is s prime of t. All right, here we go. And then the acceleration can be thought of as either the first derivative of the velocity or the second derivative of the position. And that's it. So we're done. So position, velocity, and acceleration. How do you like that? Okay, so that seems to be the end of 2.3. So what I recommend that you do is practice right here with these knowledge checks. Well, they give you the answer, but just take it out, write it out, and work on it because something what we've done in this section really does benefit from practice. So why don't you try these? If you want to, we can go over them next time. You can see this one is a product rule, and then we have two quotient rules. So, now what comes after this, by the way? I just want to remind myself. Oh, the chain rule. Oh my God. The chain rule is one of the most important results in all of calculus. It's based on what we've just got through doing, but I really don't want to start it right now. I want to start this at the beginning of a session because it's kind of involved, to say the least, but it's awfully, awfully important. We're going to see this all the time. So let's knock it off right here. I think, your head is probably spinning anyway from all of this. And just go through these examples. Make sure you can do them too. Uh, Make sure you've got the rules there. You can maybe write them down somewhere and follow along and make sure you can do these because otherwise, yeah, this is where it starts to get really intense. And so you want to make sure you know these rules by heart. Okay, by heart. So we'll stop here, and next time we'll learn about the dreaded chain rule. Okay. And we'll see that it's really not that bad. I'm making it out to be something really awful, but it just takes a little getting used to. So I'll see you then.